Bismillahirrahmanirrahim and Assalamu alaikum. My name is Kainat Shah and I am a lecturer at Civil Engineering Department, University of WA. My major subjects are geotechnical engineering, and I also teach subjects under this domain, which are foundation engineering, soil mechanics, and geotech itself. So, one of the most important and core topic under geotech is the shear strength, without which you can say geotech is incomplete. So we will be studying today the shear strength of the soil, how it is derived, where it is coming from, what equation do we use to calculate it, and how do we calculate that specific equation, and what are the other limitation for that equation we are going to go through in today's lecture. So without any further delay, let's start our slides. I'll be sharing my screen. I hope my screen will be visible to you now. Okay, so here are the contents. Firstly, we will see that how a soil takes up its shear strength, what properties are contributing towards the shear strength, how we calculate this shear strength, what is the Mohr-Coulomb theory, what is the Mohr-Coulomb shear strength equation, how it is derived, and then at the last we will be discussing Mohr-Coulomb theory's limitation. So let's move on. So firstly, we will see that there are two different types of soils. One is the coarse grain soils, which are generally termed as sand and gravels. Then there are fine grain soils, which are clay and silt. This classification is basically done on the size of the particles of a soil mass. Okay, so anything which is a passing of number 4 sieve and a retain on the number 200, that we term as sands. We generically know this. And anything which is retaining on number 4 sieve, that is a gravel. Similarly, for fine grained soils, both soils are less than 0.07 micron meter, that is the number 200 sieve, are termed as clay and silts. Okay. Then for silts, there's another certain differentiation, which is that it is smaller than in particle size than the clay particles, but it also depicts some properties of sand. For like, if I say a liquid limit property, it would be more towards sand behavior than as a clay behavior, right? Also, we can say most of the time this coarse grain soils would have particles arrangement like this, and the particle would be rounded surfaced. Okay, but in the fine grain soil there would be more flocculated structures, and the interlocking would look like this. Okay, these both type of soil would have different shear strengths basis on the basis of their properties, but every soil will drive its strength from these three parameters. Either one of the parameter would be prominent, or these three parameter would be acting in combination. So we will look into it one by one. So first one is the interlocking between the particle. This you can refer to the picture. Now see the first picture. Here the particles are rounded shape and there are air voids present, and there are large air voids present, and there's less connection between the particles as compared to the second picture. So there is low interlocking in the first picture, and there's more interlocking or high interlocking in the second picture. These are the particles which are mostly of the coarse grain soils. These are the particles which are mostly of the fine grain soils. So we can say that if there is a high interlocking, then there would be a high chance of higher shear strength values. When there will be low interlocking, then there would be lower shear strength values. So this is one of the factors. Next factor is the frictional resistance. Let's see frictional resistance, how this friction acts. So basically, when a load applies, what happens, these two particles, if you consider this, what will happen if this load is being applied? These two particles will try to slip past each other. Okay, these will try to move over each other. Now, each particle depicting a resistance towards this movement. If they resist a very good value against this applied force or applied load, then that would have a higher friction resistance. Okay, and if it's we put a very small amount of force and the particle moves, that means it has a greater amount of greater amount of friction but lower resistance. Okay, so now when the force is applied, this particle is moving this distance, while this particle is moving this distance. If it will resist more, it will have more frictional resistance. More frictional resistance will contribute towards the more shear strength. Sim- Same or similar, you can say. And this can also be interlinked to interlocking. More interlocking, more frictional resistance, right? Less interlocking, less friction resistance. So basically, frictional resistance is the property of a soil particle to resist the shearing force that is applied in result of an applied load from the external. Okay. So as in the this resistance is internal, so this would be shearing at a certain point. These particles would have a failure point, and after that they cannot resist anymore, and they will eventually shear apart or they will move. So at that point, the angle between these two particles would be called as the angle phi, which we term usually as the angle of internal friction or the angle of repose. Okay, so remember this point, as the frictional resistance can be a measure of phi, that is the angle of internal friction. Last one is the intermolecular attraction forces. Now we know that intermolecular attraction forces are of two types. One is the cohesion and other is the adhesion forces. Cohesion is a force that acts between the particles of a same material, and adhesion between two different materials, right? So when we are talking just about the soil particles, then we know that this is we talking about the cohesive forces, not the adhesive forces, right? So now again consider the soil mass box. In the first case, when the load is being applied and there was low cohesion between the particles, or let's say there was low tendency of attraction between the particles outer surfaces, then what will happen if this if there would be a shearing force due to that applied load is acting, then they will move this distance, a longer distance. Whereas if these two particles have more intermolecular forces, and then there is the same case, they will move a little distance. Okay, because now they are interconnected from their core. Okay, let's say clay has more free electrons in its outer shell, as is a flocculated structure, right? So more electrons, if are free in the outer shell, that can have more cohesion forces than with the other particles or within the same particle. That's why if you experiment, if you have, you must have experimented this at home, that if you play with clay and then you leave that clay from your hand, it still sticks at your hand even if it's in the dry state. That's because of the intermolecular attraction forces. And if we say the same behavior with the sands, sand does not stick. If we are holding sand in our fist and then we open the fist, it will flow out of our hand just like that, just like the pearls of the anything. Okay. So in sands, there are less intermolecular forces as compared to your clay particles, right? So this C, we can say this is C and this is phi, right? And this first one is the interlocking between the particles. So all these three factors, either in combination or one particularly being prominent, can be contributing towards the shear strength of these types of soil in particular, right? Now, this interlocking between the particles factor, this is a factor which needs microscopic experimentations to be measured. So as it is not measurable, we will not be considering this in on forward calculation. We will just be focusing on the frictional resistance and intermolecular forces. Now, what we will do, we will consider a soil type and then we will see from what factors it is driving its shear strength from. So, firstly, we will take the case of coarse grain soil, sands and gravels. We are taking both as the same soils because there's no such difference between their properties, right? So, in these two types of soil, the soil is driving their shear strength from interlocking and the frictional resistance, right? Now, we had said that we will not be considering the first one because it's a microscopic property. So, for coarse grain soils, the shear strength would be coming only from the phi point, right? So when it's only coming from the frictional resistance, we can say them as phi soils, or we can say them as frictional soils or cohesion less soils. Okay. Now, coming towards the second type is the fine grained soils. Now, we had discussed this before as well, that clay and silts are different when it comes to the behavior. So, we will take both of the soils separately. So, firstly, we will consider the case of silts. Silts display the property for both soils, that is, the C and Phi soils. Remember that we have said this as C and this as Phi soil. So, silt might have a angle of internal friction, that is phi angle, and it might have a cohesion value as well, so it is called as a C and phi value. So for in silts, both frictional resistant and intermolecular attractive forces are acting to contribute towards this shear strength, and also the first one, but we are not considering it in our calculations. Last one is the clay, which is pure cohesive soil, and there is no internal friction between it. So this sea soil is your cohesive soil, that is the clay, and it's the fine grained soil. Also one is acting, but again we are not measuring it. So we got that the coarse grained soils gets it shear strength from interlocking and friction resistance, or clay drives its shear strength from the interlocking between the particles and cohesive cohesion uh, cohesion cohesive strength, right? And then there is a frictional, then the third one is the silts. So silts basically drive its shear strength from the frictional resistance and intermolecular forces. Now let's see the Mohr-Coulomb's theory. To understand the Mohr-Coulomb's theory, firstly let's go through this point, that there was two scientists, one named the Mohr, another named the Coulomb. So Coulomb presented the theory at first. So he presented the idea that any shear force is a function of applied normal force. Now, to understand this point, we will consider an example of these two boxes. Okay, this box weighs 2 kg and this box weighs 200 kg. So, and we know that our weights always act in the downward direction. Any force that is acting downward direction in a soil mass, we term this as sigma. Okay, normal stress. Okay, so this 202 kg is the sigma n value. And this horizontal force acting here, which is trying to push this box, is termed as tau value. Okay. So it's very obvious that when the weight is 2 kg, it's easier to push this box as compared to when it weighs 200 kg. It will require more more sharing or push force to move it from one place to another. Okay. So similarly, Coulomb presented this function as tau f, a function of sigma. Tau is the value of shear stress and sigma is the value of normal stress. Now, how do we calculate the value or the equation for the shear strength from this function? Let's try this uh, case for C and Phi soils. For the cohesion less soils and the pure cohesive soils, we will see in the limitation section what we do for those kind of soils. For driving the Mohr-Coulomb shear strength equation, we will be considering the case for C and Phi soils because it's depicting the more perspective of the overall soils. So firstly, we mentioned this relation here. Then we will be plotting its graph. So now we know that y is always a function of x, and this is our x-axis, and this is our y-axis. So on x-axis, we will plot sigma, and on y-axis, we will be plotting tau f or the shear strength values, right? Now let's consider example that our soil has a certain normal load, that is sigma n, and it has a certain cohesive strength, which is also a strength parameter. So we will be plotting it on the y-axis. So it's its internal property C value, and this is sigma n. Both these properties So these are its internal properties, cohesion and sigma n values. Both these properties will be made by lab experimentations, right? So according to this function, what happens when the sigma n increases in this direction, or tau value should be increased in a linear pattern. So after this point, as per this function, what happens when the sigma n increases in this direction, the tau value should be increased linearly with sigma n. Now we will start our graph from this point, because till this 0 to this point is the value for your cohesive strength. Now we draw a linear line for our tau measurement, right? So this line is depicting then when we are increasing the normal stress, the tau value or the shear strength value is also increasing in a linear pattern. Now what we will do, we will translate these two parameter on the next axis. Sigma n translated above, and again sigma c translated laterally. Now what will I do? I'll join this point to the point on the x-axis. So we can calculate this total amount of tau f. There you go. Now you can see this is a right angle triangle, and we have a value for the base. So to calculate this portion, because half of the portion we have to calculate the tau f value, but for this portion we need to have either the this hypotenuse value to use the trigonometry formula, or we need to have this angle of friction. Now, how can this be an angle of friction? Because we know this shear strength and the normal strength in a combination would be acting on a certain angle where the soil would be failing at. Okay, so this angle must be angle phi. So now we have the angle, we have the base. We will use this basic trigonometry formula and we will calculate this segment as sigma n into tan phi. Now adding these two parameters, we can calculate the tau f equation, that is C plus sigma n tan phi, and we know this is the equation of shear strength. So tau f is basically your shear strength value, C is the cohesion, sigma n is the normal stress, and phi is the angle of friction provided. Now this equation was presented by Coulomb with the perspective of total stresses. Another scientist, Moher, came in and he did some modifications, and he said that no, you cannot apply it to the total stresses. You have to apply the equation for the effective stresses. What are the effective stresses now? Is that sigma dash is equals to total sigma minus pore water. Okay. When we are specifically seeing how much load the soil solids are carrying and not the voids filled with water, then we are taking the dash values, okay, for the cohesion, for your sigma and your phi value, right? When you are canceling out the effect of pore water pressures, then you are using the effective stresses. So basically Mohr did the modified equation for calculation, which is in use till now, is tau f c dash plus sigma dash tan phi dash. So these are the basic effective stresses. Now we know that this F depicts the failure point. Okay, so this tau would be the shear strength at its failure, that it would be the ultimate shear strength we are calculating. But we also know that soil with a certain load will not be at its failure condition or at its peak value of shear strength. It would be depicting either low value of shear strength or the higher value, maybe higher value than the tau f value. So how will we calculate that tau instant or normal tau value? This is tau f at the failure condition. Then a certain soil would have a this tau value. So how will we calculate that? For that we will consider another example of foundation which is being laid on a soil surface. Now this foundation would be having some load in this direction, which should be sigma, and we call this sigma as del sigma, or we say it as a surcharge load, right? Now what we will do, we will consider a point or a soil particle under this foundation. Now what will I do? I will enlarge this as this point, okay? Now if this particle is this square particle, then what will be happening on it? There would be two types of forces acting on it. One in the horizontal downward direction, which we will call as sigma 1. It is coming from the load from the foundation. And second would be the lateral pressure, that is the confining pressure, which will be coming from the other particles which are trying to compress and trying to keep that particle in its place. So this sigma 1 and sigma 3 are called as major and minor principal stresses respectively. This we will be using in our next lecture, but we should know. So considering this figure, let's assume that it will fail at a certain angle or at this failure plane. Okay, I just draw a line. I said that is this soil, this soil particle would be failing at this line. Now this line would have a certain angle. Can we call it as a angle of friction? No, we cannot call it as angle of friction or the phi angle, because we don't know if this line is the real failure plane or not. We are just still assuming that it could be the failure plane. So for now, we will be calling it as alpha and not as phi. Now this shear value would have its component sigma n and tau. To calculate this sigma n and tau, we have these formulas. So from this formula, we will calculate the value of normal tau or the instant tau for this condition. Then what we will do, we will compare that tau value with our final shear strength value or the tau F value, and we will see if it's greater than it or if it's less than it. If it's greater than it, then the soil particle will not collapse and it will not shear away and it will be safe. If this tau F value is less than tau value, that it is unsafe and this particle will further crash or it will deform itself into smaller particle. Okay, so here is the use of the tau F value. Tau F is the basically ultimate, and tau value should be the allowable or the instant tau shear stress value. Coming towards the last point of our lecture today is the limitation of the Mohr column. As we know, the Mohr-Coulom's theory and Mohr-Coulom's equation is derived based on the C and phi soils, that are the sill soils. But what for the cohesive soils and what happens when it's the non-cohesive soils or the cohesionless soils? So firstly, let's see for cohesive soils. When we consider the cohesive soils, then our tau F becomes C plus sigma 10 phi. This becomes 0. Okay, so our tau F remains for this one, but this will calculate as a constant value. So can it be that our shear strength be a constant value? No, it cannot be true. Why? Because that would mean that if this is a soil surface, then a point here, a point here, and a point here, they all would have the value of 5 for shear strength. Can it be possible? No, it cannot be possible. It could be possible that it is 2.2, it is zero point 0.5, and it's zero point 0.8. Okay, this could be possible, but not what it's saying. Okay, so shear strength within the depth, your shear strength for the cohesive soils changes. Even for the cohesive soils changes, right? It cannot be constant along the depth or along the lateral forces, right? So this cannot be true in case of cohesive soils. So this is one limitation. And for the cohesionless soils, again, let's see what our tau F becomes. C is 0 plus sigma 10 phi. Okay. And as previously we have seen that the sigma is basically sigma dash. Okay. That is the effective stress. We are not considering the effect of pore water pressure. And now let's again take an example that we are moving on a floor or on the very surface of the soil. Now where the total the stress would be the total stress and not the effective stress, because there would be no pressure, pore water pressure, there would be no pore water pressure on the ground surface, right? So there would be the sigma dash is equals to 0 if on the ground. That means this terms can also be 0 on ground. So can it be possible? No, it cannot be possible. Why? Because if this is zero, that means the shear strength of the soil at the surface is zero. That means if we place a foot on the soil, it will start to move because it will be behaving like the water particles. Water doesn't have shear strength. Shear strength is zero. So that's why it's flowing. So what will happen if the shear strength of the soil on the ground is zero? Then if we will put a foot, it will start moving, and that is not true. So these are the two limitations for our cohesionless and cohesive soils which Mohr column does not incorporate in its equation. But we still use this equation in our practice. And also, when we have to consider the case for cohesive soils or the cohesionless soil, we make certain assumptions and we mention these limitations in the end of the question or the design, that okay, we had the cohesive soils, but we are limited to Mohr column. So this is the best approximation we are doing. Make a good factor of safety and further do your require so for designing something or calculating the settlement or anything related to geotech, right? So basically, we had to cover up till this point in today's lecture. In next lecture, we will be seeing how principal stresses are calculated using Mohr circle and how Mohr cycle actually benefit us to calculate the shear strength of the soil using drawing tools, okay, and not the equations. So for now, thank you so much for attending the lecture. If anybody has any kind of question, please feel free to email me and have a good weekend. Thank you so much. Allah Hafiz.